One of the main skills you come away with from a differential calculus class is learning how to differentiate, learning how to build these machines that will tell you the slope of a function at any valid point. So far, this is from the results of calculus PDF that you guys all have available on Canvas. Everything here underlined in light blue are things that we have proven. So all of these light blue underlines are things that we have proven either in class or in these videos. And the things in dark blue, so here, and these guys are things we haven't quite gotten to yet. These ones are not hard. In fact, we will indirectly sort of prove, well, at least show how to prove these two in this video. Try pinning when we prove that. In other words, if we ever in this video take the derivative of some random number to the power of x, so zoning in over here. So if we ever have to take the derivative of like 7 to the power of x or 5 to the power of x, which we might have to in this video, watch how we do it, because if we know how to do it for a particular number, then we'll actually be able to generalize to a arbitrary number, as long as the number is valid. Same thing here. If we want to take the derivative of log base 5 or log base 3 or something, we can use these other tools to do it, and you'll see how that happens. And notice that I have these underlined in blue, like the derivative of cosecant is negative cosecant cotangent. I can't remember if we've actually proven them, but to be honest, all of these can be proven with the quotient rule. So we have the quotient rule. That's one of the things that we have proven. So try it on your own to show the derivative of those guys. But all this to say is, if it's underlined in blue, then I will definitely do it without proof. If it is not underlined in blue, then I might pause and kind of show that this is true in this video. All this video is going to be is kind of like a derivative marathon. I have 10 different derivatives set up, and we are going to take their derivative. In other words, this is going to be a video about how to build slope machines. That's pretty much what this is. Great skill, or probably one of the most important skills of a calculus student, at least a first-year calculus student. That's what you guys are, is how to find derivatives. So let's see what we got on the docket here. All right, starting with this guy. Few observations. I am seeing a quotient. So in my head, I'm thinking, the quotient rule probably will be useful. Turns out there's actually a few ways to do this. I will start with the quotient rule. And to make this video go as smooth as possible, that results of calculus PDF should be next to you as we crush these. So method 1, quotient rule. And I'll treat the first few of these derivatives as if I'm talking to complete newbies, but hopefully at this point you guys have already had a bunch of practice with derivative taking, so you could probably skip a lot of the steps that I am choosing to do here. So I'm going to rewrite S, and I'd like to use the quotient rule. In other words, in my brain, I know that A over B prime is equal to B prime times A minus B times A prime, all divided by, that's also just not true. Hold on. Do I even know the quotient rule? B times A prime, you probably were screaming at me on the other side of the screen, minus B prime times A, all divided by B squared. So I know this. So what I'm going to do is simply name some stuff here. It looks like I can name this guy A and this guy B, which would mean that S prime is equal to A over B prime, but I know what that is. That's going to be low D high minus high D low, all divided by low squared. So I really just need to find two pieces. I need to figure out what A prime is and what B prime is. So A is equal to 1. Oh, but that's easy. A prime must be equal to 0. B is equal to root T minus 1. Oh, but that means that b prime is equal to, this negative 1 is going to disappear when we take the derivative. It's a constant. And we have the derivative of a sum is the sum of derivatives. So this second function, quote unquote, here will be 0 when we take its derivative. And the square root of t is something we've done many times. So b prime is 1 over 2 root t. And therefore, s prime, which is what we're trying to evaluate, is b, which is this, times a prime, which is 0, minus a, which is 1, times b prime, which is 1 over 2 root t, all divided by b squared. This is gone. That's 0. So what I have is negative 1 over 2 root t divided by root t minus 1, all squared. And we should know how to do fractions. That's negative 1 over 2 root t times root t minus 1, all squared. Done. Method 2. What I'm going to do is force chain rule into this. Notice that s is the same thing as 1 over root t minus 1, but that's the same thing as root t minus 1 to the negative 1 power. Remember your exponent rules. And then all of a sudden, to take the derivative, all I have to do is follow the chain rule. So I see an outside function here. Maybe before I do this, since this is kind of like how to do it, let's notice that if I say f of t, say, is equal to t to the negative 1, and g of t is equal to the square root of t minus 1, I did not need those parentheses, then s is equal to f of g of t. Okay, so notice that if I grabbed this function, plugged it in for t, in other words, every time I saw a t here, I would replace it with g of t, that would create s. This is the same thing as s. So this is the same thing as s, which means that to take its derivative, I just have to follow the chain rule. S prime is the same thing as f prime of g of t times g prime of t. Oh, but I can figure out all of these things. So s prime is the same thing as f prime. So f prime of t, looking here, that's the power rule. Negative t to the negative 2. And also g prime of t, we've already evaluated that, 1 over 2 root t. So just plugging things in, I need to look at f prime of t right here and plug in g of t. That's what this first piece is. So that's going to look like this. Negative g of t to the negative 2, but g of t is the square root of t minus 1 to the negative 2, times g prime of t, that's 1 over 2 root t. So this is the same thing as negative root t minus 1 to the negative 2, all divided by 2 root t. And with your exponent rules, that's going to be the same thing as negative 1 over 2 root t times root t minus 1 squared. And that is indeed the same thing I got the first time. All right, so 2 different methods for the same question. You guys can choose your tactic. Next function. Okay, wow. So we definitely got some chain rule here. In fact, we got the composition of 3 different functions. For my first approach, what I am going to do, this will speed up here in a second, but I am going to do the first few derivatives, like showing a lot of steps and how you should approach these for the first few times. So what I'm going to do is say that a of theta, let's just call it, it seems like I want to do the outermost function. So I want to write R as the composition of functions. I actually see 3 different functions. it could be even more than that, that r can be expressed as. Let's see. So I want to ask myself, what is the outermost function? And I'd say a of theta is equal to theta squared. And then I could say that b of theta, or whatever, is equal to sine of theta, because that's going to be the next innermost question. I'm seeing the outermost is something squared. Then I go inside a little bit more. Maybe it's better if we kind of rewrite this. This is, by the way, the same thing as sine of theta plus root theta plus 1 all squared. That's what this 2 here means. So the outermost function is something squared. The next innermost is sine of something. And then we have the final innermost, well, what I'm going to call the final innermost. It's c of theta is equal to theta plus root theta plus 1. Okay, and so let's see. What I think I just showed is that r is actually equal to a of b of c of theta. So think about why that's true. Notice what happens if I grab this function and plug it in right here where this theta is. Then I would have sine of this huge thing. Oh, sweet, that's what I have on the inside right here. But then what happens if I grab that whole new thing and plug it into this guy? That's going to create the original function r. In other words, r is the composition of these three functions. And of course, I can't go further here. C is kind of like awkwardly the composition of two other functions. Specifically, it's the sum of an easy function, theta, and then another function that is the composition of two other functions. So C is kind of gross. So what I really need is to take three derivatives. I need a prime of theta. That's easy. That's 2 theta. And then I need b prime of theta. That's also easy. That's cosine of theta. And then I need c prime of theta, the hardest of these three. That's going to be 1 plus 1 divided by 2 times the square root of theta plus 1. Okay, so I just used the chain rule just on this part. But then I need to multiply by the derivative of the inside part here, the theta plus 1. The derivative of theta plus 1 with respect to theta is just 1. So that is going to leave me just with this part right here. Now, all those pieces are going to come into play when I take the derivative of r. So the extended chain rule will say that what I have to do to find r prime is take the derivative of the outside function and evaluate it at the inside function. So notice it's kind of like I have the outside function a, and then this whole inside part is the inside function. But then what I need to do is take the derivative or multiply by the derivative of the inside function. In other words, I need to multiply by the derivative of b of c of theta. I guess I'll write it down. But how do I do that? That's the chain rule again. So what I have is a prime of b of c of theta times b prime of c of theta, again, chain rule here, times, last but not least, c prime of theta. So now I ask myself, how do I find these three pieces? Well, a prime is 2 times theta. But what I'm going to plug in for theta here is b of c of theta. In other words, I need to grab c of theta, this guy, plug it into b. So grab this thing, plug it in for theta. That's going to create sine of this huge thing, right? And then plug that into this. Okay. So what that's going to look like, this is the same thing as 2 times the sine. Okay, again, so that 2 comes from right here. I'm replacing theta with b of c of theta. And b of c of theta is going to be sine of c of theta, if you so choose. But c of theta is theta plus root theta plus 1. Okay? And then I multiply by b prime of c of theta, but b prime is sitting right here. So then I multiply by the cosine of c of theta. What that means is I grab c as if nothing happened to it and plug it in to b prime of theta. That's my hand rubbing the iPad, making funny noises. Okay. Now, last but not least, so here, just to make sure things are clear, and you should think about why these are true. This takes practice. And then we have this last one, c prime of theta, but that part's easy. Because it's literally just c prime of theta. So 1 plus 1 over 2 root theta plus 1. And you might ask yourself if there's an easier way to write this or a cleaner way to write this. I don't know. I guess if you have the sum of two things. So here's how I'll write this. Probably the easiest. This is the same thing. Is that even better? Yeah, maybe. 2 times sine of theta plus root theta plus 1 times the cosine of theta plus root theta plus 1 times 2 root theta plus 1 all divided by 2. Is this good? Yeah. 2 root theta plus 1. And then these 2's can cancel. Nice. All right. Let's try another one. Oh, I'm crowding into my other image here. So I don't know. Maybe we'll take this down here. So it looks like I got z is equal to 4y cubed minus 1 cubed, all divided by 3y plus 5 to the 4th power. Okay, I'm wondering if this is a good stage for me to kind of speed up the process. I don't know. I'll do maybe one more kind of showing what I'm thinking. There's a few things I could do. What I'm immediately thinking about doing is the quotient rule. I'm going to name this top thing A, this bottom thing B. And notice that for each A and B, I will have to use the chain rule to find A prime. So if A is equal to 4y cubed minus 1 cubed, that means that A prime is equal to, I have to take the derivative of the outside function, that's something cubed, so it's going to be 3 times 3 times 4y cubed minus 1 squared, all right, times the derivative of the inside function. So the inside function is actually going to be just the thing on the inside of the parentheses. The derivative of that is not too bad. What is that? That's 12y squared times 12y squared. So this is the same thing as 36y squared times 4y cubed minus 1 squared. And talking about b, so b is the same thing as 3y plus 5 to the 4th power, but that means that b prime is equal to, so I have something raised to the 4th power on the outside, so that means I need to use the power rule. This 4 comes out front, and you decrease the exponent by 1, and then you have to multiply by the derivative of the inside part. So the inside part here is 3y plus 5. And that is going to be the derivative of 3y plus 5. That's simply what is the slope of a line that looks like 3y plus 5? That's going to be 3. So this is equal to 12, 3y plus 5 to the 4th power. All right. But check this out. I know that z is equal to a over b, which means that z prime is equal to a over b prime, which is equal to, low, D high, minus high. See, I said low, and then I put a tick mark on it. Minus high, D low, all divided by low squared. And now it's just plugging stuff in properly. And hopefully something nice happens. I think something nice will happen. So we got B, which sits right here. So that's going to be 3y plus 5 to the 4th power times A prime. So that's 36y squared times 4y cubed minus 1 squared. So that's my A prime. And then minus A is 4y cubed minus 1 cubed times B prime, which is this guy right here. 12 times 3y plus 5 to the 4th power. To the 3rd power. I don't know why I put a 4 here. That's a problem. I was like, that doesn't make sense. 3rd power. 3rd power. I was like, the power can't just stay the same. 3rd power. Oh my gosh. Wrong colors. 3rd power. All right. All divided by b squared. B is, okay, so that's going to be 3y plus 5. And it's to the 4th power. That is going to be 8 to the 8th power. What I'm going to do is I'm going to notice some common things. So this is the same thing as 3. I'm noticing common terms from the numerator. So let's see the best I can do here. Okay, so what's common? I think a 12 is common in the numerator. So I'm going to take a 12 out. I think a 4y cubed minus 1 squared is common. So 4y cubed minus 1 squared. And then I also have a 3y plus 5 cubed. That's in common. And what's left, let's check this out. So I still have a 3, because I factored out a 12, and I still have a y squared. And I still have one of these things. So it's going to be 3y squared. And then I have one of the 3y plus 5s. And then over here, let's see what I've taken out. I've taken out 2 of these guys. I took out that 12. And I still have... Wait, hold on. Let me look. I feel like I messed something up. Did I? Low, D high, minus high, D low? No? Oh, okay. So, yeah. I still have one of these hanging out. This whole thing was taken. So, what I have is minus 4y cubed minus 1, all divided by 3y plus 5 to the 8th power. Okay, let me double check myself. Yep, I think that all looks good. If you don't believe me, just redistribute this chunk through these both of these pieces, and it should be the same thing. Okay, so hopefully we're all noticing that this is going to cancel with 3 of these. And I think that's it. So my final answer here is going to be 12 4y cubed minus 1 squared times 9y cubed. Oh, no. Okay, so maybe this won't be my final answer. Plus 15y squared plus 1 minus 4y cubed, all divided by 3y plus 5 to the 5th power. I got to work on my 5s. So what we have is 12 times 4y cubed minus 1 squared. And then these guys simplify. The y cubed simplify to 5y cubed plus 15y squared plus 1 all divided by 3y plus 5 to the power of 5, and that's a nice answer. Okay, let's keep going. All right, so we got chain rule, we got product rule, and we have derivative of a tangent here. Okay, so there's a few things I can do. It looks like we're kind of hinting at using the power rule for the integers. So let's do that. I have that L prime is equal to, what I need to do, I guess I'll do, since this is the first product rule for the video, I'll label things. So let's do A and B. That means that L prime is equal to A prime times B plus A times B prime, which means I have two pieces to find. If A is equal to m to the negative 3, that means that A prime is equal to negative 3 times m, negative 3 times m to the negative 4. That is the power rule for the integers. If if B is equal to tangent squared of m to the 5th, what that means is I have chain rule 3 times over. The outermost function is something squared. The next innermost is tangent of something. And the final innermost is m to the 5th power. Now, what that means is that B prime, my first move is the derivative of the outermost function. That's going to be something squared, which is 2 times whatever was squared in terms of the chain rule here. So what's on the inside is going to be tangent of m to the 5th. All right. And then I have to multiply by the derivative with respect to m of the tangent of m to the 5th. Okay. But shoot, we know what the derivative of tangent is. So this is the same thing as 2 times the tangent of m to the 5th times secant squared of m to the 5th times the derivative with respect to m of m to the 5th. Okay. Now, final answer. This is going to be the derivative of m to the 5th is 5m to the 4th. So what I have is 10m to the 4th times tangent of m to the 5th times the secant squared of m to the 5th. Okay, so that was chain rule. And like I said, we did that a lot faster than the prior example. It truly just takes practice. Checking your work in the back of the book, checking your work with classmates, checking your work on Symbol Lab, or with ChatGPT or whatever. I wouldn't trust that one that much. But we have all the pieces we need. We have A prime, we have B prime, we have A, we have B, and we can find what L prime is. We have A prime first, that's negative 3. I'm not going to have room. This is equal to A prime, that's negative 3, m to the negative 4, times B, which is tangent squared of m to the 5th, plus A, which is m to the negative 3, times this whole function right here, which is 10m to the 4th. Oh, I'm seeing something nice. That's m to the 4th, times tangent of m to the 5th, times secant squared of m to the 5th. Let me use some colors to kind of make sure all of our eyes are going to the right places. A prime. We have B. We have A. And we have B prime, which is this piece. Okay, so hopefully that's sort of clear on how we're piecing things together. Let's see if we can simplify. I think we can, especially right here, because we have this m to the negative 3 and m to the 4th. That's going to simplify to m to the first power. And also, we probably should find common terms. Maybe. Does that make anything look better? Let me think here. I can bring everything in terms of tangents. I can take out... I want this to look as good as possible. Let's see. All right, here's what I'm going to do. This is the same thing as... Yep. Tangent of m to the 5th over m to the 4th times... All right, watch this. Make sure I'm right. 10 m to the 5th times secant squared of m to the 5th minus 3 tangent of m to the 5th. All right. I think that might look slightly better. I don't know. It's kind of all the same. All right, there you go. Next, let's see what's going on. All right, so this looks like a simple product rule, a little bit of chain rule going on. Okay, let's call this A. Let's call this B. I said I was going to kind of give this up and just start taking derivatives, but I guess this is an like how to differentiate video, so that's fine. We got A is the same thing as 10 times e to the negative 1/5 times x. Okay, I rewrote that a little bit. Because if I want to take the derivative of this, first of all, the 10's just going to hang out. And then I have the composition of two functions. That's going to be e to the power of something times negative 1/5 x. So what I have to do is take the derivative of e to the power of something, but we all know that's just e to that thing. Then I have to multiply by the derivative with respect to x of negative 1/5 x. All right. But that is the same thing as, so 10 times, this is just negative 1/5. So 10 times negative 1/5 is negative 2 e to the negative 1/5 x. All right. So that all simplifies to just that. And then I have b is equal to the cosine of 7x. I have an outside function, and that's the cosine of something. The derivative of the cosine of something is negative sine of that thing times the derivative of 7x, but that's just 7. So, of course, that can be rewritten as negative 7 sine of 7x. And now this is just, what does the product rule say? So we have y prime is equal to a prime times b plus a times b prime. And what we got is just plugging stuff in. That's easy. It's easy enough. So this is the same thing as negative 2 e to the negative 1/5 x times b cosine of 7x plus a, which is 10 times e to the negative 1/5 x times b prime, which is negative 7 sine of 7x. Then we ask if we can make this look a little bit better. Is there any common terms? There certainly is. I'm going to take out a negative 2 e to the negative 1/5 x. That's going to leave me on the inside with the cosine of 7x plus 35 sine of 7x. Fact check me, please. But I think that looks good. All right, that one wasn't too bad. All right, next we got W. Oh, geez, this one's definitely going to be a problem. So we have the natural log of this thing. I'll go ahead and start and say, well, the first step's not too bad. W prime, the outermost function is the natural log of something. That's actually one of the easier derivatives. It's just going to be 1 over that thing. Secant of 3 theta. And what I then need to do is multiply by the derivative of that thing on the inside of the natural log, which is 5 times e to the negative 2 theta times the secant of 3 theta. All right. This is going to be the big side quest. We have to pause and figure out what this is because this is in itself a product rule. All right. So let me name this, maybe, this part right here. Let's name this A, and let's name this B. So A is equal to 5 times e to the negative 2 theta. We got B, which is equal to the secant of 3 theta. And to literally find the derivative of A and B, we have to use the chain rule. So all sorts of derivative rules that we got to use all at once. This is something we're getting used to. This should you should get to a point where taking derivatives or differentiating synonymous phrases is very just second nature. Like you don't have to think that hard to do it. All right, so for instance, in here we have A prime is equal to 5 just hangs out. I have e to the something, which means that the derivative of that part is going to be e to that thing. And then I have to multiply by the derivative of that thing. So the derivative of negative 2 theta is negative 2. Derivative with respect to theta. In a similar fashion, I have an outermost function, which is the secant of something. I know that to be the secant of that thing times the tangent of that thing. Then I have to multiply by the derivative of 3 theta, which is 3. So B prime is equal to 3 secant 3 theta tangent 3 theta. And that tells me that the derivative of this object, so this whole thing, maybe I'll come up here, is going to be A prime times B plus A times B prime. And that is equal to A prime, which is negative 10 e to the negative 2 theta. I just cleaned this up a little bit. Times B, which is secant of 3 theta, plus, okay, board management, bottom tier, plus A, which is 5 times e to the negative 2 theta, times the derivative of B, which is this right here, 3 secant 3 theta, tangent of 3 theta. So overall, that's going to be equal to 5 e to the negative 2 theta, 3 secant, I can also take out a secant 3 theta, times secant of 3 theta. And what's left over here, so what I just factored out was one of these 5 e to the negative 2 thetas and a secant of 3 theta, which means all that's left here is a negative 2, and all that's left here is a 3 tangent of theta. Tangent of 3 theta, I mean. Just kind of scanning that to make sure that makes sense. Yep, that looks good. I wonder if something nice happens here, because my original function, I have to plug this thing. This part right here is this part. Like, so this whole part here, the derivative here is this. So this is all equal to, I'm going to put this in the numerator. I wonder if something nice happens. And yeah, something really nice happens. Oh, wow. How nice. Logarithms just have kind of a little bit of magic about them. And there is certainly a big reason why, because this is, okay, I'll show all steps. 5e to the negative 2 theta times secant of 3 theta times the 3 times the tangent. This should be close parentheses there. Tangent of 3 theta minus 2, all divided by 5e to the negative 2 theta times the secant of 3 theta. And yes, indeed, this cancels, this cancels, this cancels. And what all we got is 3 tangent of 3 theta minus 2. Final answer. Cleaned up nice. Oh, gosh. Yeah, so as I said, there's something magic that kind of happens with the natural log. And I am thinking we're probably going to want to use that magic in this case. Indeed, what I'm going to do, what we need is y prime here. In order to do that, what I'm going to do is force the natural log to be involved here. In other words, I'm going to take the natural log of both sides. So what we have is the natural log of y is equal to the natural log of the cubed root of this mess, atrocious mess. This is where I'm hoping everybody remembers their algebra 1, or excuse me, algebra 2. I'd be impressed if you talked about logarithms in algebra 1. Pre-calculus, if you will. Okay, before we do anything, we are going to use some logarithm rules. This is the same thing. So the natural log of y is equal to the natural log of this whole thing, x times x plus 1 times x minus 2, all divided by x squared plus 1 times 2x plus 3, all raised to the 1/3 power. Okay, so that's not a logarithm rule yet, but it is simply an exponent rule. But we now can use a logarithm rule and say that this is the same thing as the natural log of y, and it equals this 1/3 comes out front of the logarithm. That's not calculus, that's algebra 2 definition, or it's a log property. So we have 1/3 of the natural log of this mess. By the way, what we could have done from the beginning is done the quotient rule, the chain rule, but that would have been horrendous. So the logarithm kind of comes in to save the day here. Oh, but check this out. Multiplying both sides by 3. We also can do this. This is the same thing as the natural log of x times x minus 1 times x minus 2 minus the natural log of x squared plus 1 times 2x plus 3. And I'll reference the log rules that I'm using here. So this one is because of a famous log rule. The natural log of a to the power of b is equal to b times the natural log of a. Really crucial. This thing right here, this is the same thing as the natural log, or what rule I used was the natural log of a over b is the same thing as the natural log of a minus the natural log of b. All right. Hopefully that was proven in your pre-calculus class. It's not too bad. Just let me know if you want to see a proof. But you guys, the joy doesn't stop there. What we have is 3 times the natural log of y is equal to, in parentheses, the natural log of x plus the natural log of x minus 1 plus the natural log of x minus 2 minus, in parentheses, the natural log of x squared plus 1 plus the natural log of 2x plus 3. You might be thinking to yourself, how is this making anything better? Because we're about to be able to take a derivative much easier. So this rule is the natural log of a times b is equal to the natural log of a plus the natural log of b. And all logarithms hold these properties. It's not like the natural log is special or anything, but this happens to be a natural log. All right, you guys. Now we can maybe distribute So this tells us that 3 times the natural log of y is equal to the natural log of x plus the natural log of x minus 1 plus the natural log of x minus 2 minus the natural log of x squared plus 1 minus the natural log of 2x plus 3. Taking derivatives on both sides. On this side, I have 3 times 1 over y, the natural log of something. The derivative of the natural log of something is 1 over that thing. But then I have to multiply by the derivative of that thing. And then look at these. Each of these individually are not hard to take the derivative of. I have the natural log of x. I already know what that one is. That's 1 over x plus the natural log of x minus 1. If I want to take its derivative, I would have 1 over x minus 1 times the derivative of x minus 1. But that's just 1. Okay? And then I would have plus the natural log of the derivative of the natural log of x minus 2. That's going to be 1 over x minus 2. And let's see. Over here, what I have is minus 2x over x squared plus 1. Then here is minus 2 times 2x plus 3. Try to see why that's true. I did follow the chain rule on both of those guys. Okay, again, what I want is y by itself. And I'm starting to think, hopefully there's something nice that's about to... There should be like some sort of cancellation that happens here. Multiply both sides by y. Well, I guess this is okay. So what I have is 3 times y prime is equal to y times this sum. Okay, and then we have 3 y prime is equal to, oh, check this out. Wait, is this nice? Hold on. Y prime is equal to y, but y was the cubed root of all this craziness. All divided by okay, so the process is cleaned up by taking the logarithm on both sides. So I have y prime is equal to 1/3 this guy, cubed root of x times x minus 1 times x minus 2, all divided by x squared plus 1 to x plus 3, and then I have this sum. All right. So that might not look amazing, but at least we were able to solve it somewhat decently, quickly. Okay, so remember your log rules. That's the big takeaway. Those will help. In fact, I think this is a perfect example of when we want to use our log rules. Huge fact. A second ago, I think it was in the theory video, I told everybody that if we had e to the star was equal to square, That's true if and only if the natural log of square is equal to star. But let's notice this. I have that star is apparently also known as the natural log of square. So how about I replace this star with the natural log of square to see what shows up. Whoa, that's crazy. So what that says is that I can write anything. So here's just a square. I can write anything as e to the natural log of that thing. So for instance, 7 is the same thing as e to the natural log of 7. It's kind of like these functions cancel each other out. And indeed, that's what they do. If I have, I don't know, pi to the power of 2, that's the same thing as e to the natural log of pi to the power of 2. This goes in both directions also for this formula. Notice that this thing, I have a square, but another way to say square is apparently e to the star. So what this says is the natural log of e to the star is equal to star. All right, so that's just substituting square in for my natural log expression. So the natural log of e to the 7th power is equal to 7. The natural log of e is equal to 1 because e is also expressed as e to the 1st power. Why am I saying any of this? Because you might look at this function and go, oh, okay, it's the power rule. We have that v prime is the same thing as sine of q times q to the power of sine q minus 1. This is an atrocious mistake. Why? Because the sine of q is not a constant. All right, so constant, the power rule only works if you are if you have a variable raised to a number. So we have to use these tools that I've been hinting at in order to find the derivative here. What we can do is rewrite v as e to the power of the natural log of q to the power of the sine of q. Okay, so again, it's kind of like this is my square. So this is kind of, here, I can write it like this. Square is equal to e to the natural log of square. All right, but I know I know the power rule for the logarithm. That's kind of horrible. I know my log rules is what I should say, and this sine of q can come out outside of the logarithm. So this is the same thing as e to the sine of q times the natural log of q. And this is something I actually can take the derivative of. V prime is going to equal the derivative of the outside function, but that outside function is simply e to the something. So what I begin with is e to the power of sine q times the natural log of q. All right, again, I just took the derivative of e to the something, but then I have to multiply that by the derivative with respect to q of the inside function. What is that inside function? Sine q times the natural log of q. But that's the product of two functions, ladies and gents. That's easy differentiating. What I have is e to the sine of q times the natural log of q. The derivative of the first function, cosine of q, times the second, natural log of q, plus the first function, sine of q, times the derivative of the second, which is 1 over q, natural log of the derivative of the natural log. And I'm already almost done. This is the same thing as e to the sine of q. Okay, so, but this e to the sine of q, natural log of q, is the same thing as v. So what I'm actually going to write at the beginning is just v. This is the same thing as v times, it looks like I have q times the cosine of q times the natural log of q plus the sine of q, all divided by q. That's a q. All I did was find common denominators. And you really shouldn't have the dependent variable mixed in with the independent variable, but luckily we know that v is also the same thing as q to the sine of q. And this could sort of be my final answer. What I have is q to the sine of q minus 1 times q cosine of q natural log of q plus sine of q. Nice. Okay. How many more of this we got? 1, 2. Okay, we're almost done. All right, you guys, this is just an abuse of chain rule, to be honest. What I'm going to do is, I guess, square both sides. Can I do that? Is that the best way to do this? Yeah, probably. No, I'm just going to force chain rule this guy. So I think y prime is the same thing as 1 over. My outermost function is this square root of something. So that's going to be 1 over 2 times the square root of the natural log of the square root of the natural log of the square root of x. So annoying. Which is the same thing as y. Times the derivative of the natural log of the square root of natural log of the square root of x. But that's just going to be 1 over the natural log, or excuse me, careful, I'm talking to myself. 1 over the square root of the natural log of the square root of x. Okay, so I just took the derivative of this red function. That's the stage I'm at right now. The derivative of the natural log of something is 1 over that thing. So that's what I have right here. But then I have to multiply by the derivative of this blue function, because that was on the inside of the natural log. So the derivative of that blue function is the derivative of the square root. So that's going to be 1 over 2 times the square root of this function that was on the inside. So this function, 1 over the square root of the natural log of the square root of x. And then I have to take the derivative of this yellow function. So this whole yellow function, the natural log of the square root of x. And you could use a log rule here, but I'm just going to force it. That's going to be 1 over the square root of x. And last but not least, I have to multiply. What color am I at? What color can I use? Green. The derivative of the square root of x. But that's hopefully easy enough for everybody in here. That's going to be 1 over 2 root x. Wow, what an insane time. Let's see. So we have 1 square root. I also am noticing that I have 1/8. So collecting the 2's, 2, 2, and 2, that's going to be 1/8. And I have root x and root x. Okay, so that's going to come out to an x. But then I also have the square root of the natural log of x times the square root of the natural log of x right here. That's going to come out to the natural log of the square root of x. And then I think that's it, because these two roots come together to be x. These two blue things come together to be just this blue thing. And then all the red comes together to be this 8 right here. And all I have left is this yellow object right there. So that's going to be the square root of the natural log of the square root of the natural log of the square root of x. What an obnoxious question. It's kind of fun, though. This taking derivative nonsense. Okay, so let's see. Last one, it looks like. Last one today. Yep. All right, so this is going to be very similar to something we've seen before. I think I'm going to rewrite this guy as e to the power of the natural log of 7 to the power of the square root of tangent of z. Okay? That's this sort of square and star situation that we had going on over here. I'm using that again. I can rewrite any object, any square, any object as e to the power of the natural log of that object. But I also have this one. I can rewrite any object as the natural log of e to the power of that thing. In particular, this one, so what I have is the natural log of, is this one going to be useful? Oh, no. Here's what I want to do for this one. Okay, so that's not what I want to do. But what I do want to do is this. there is this thing called the change of base formula. The natural log, or I can do, let's say this, the log base A of anything can be rewritten as the natural log of that thing divided by the natural log of A. Yeah, that's right. Let's see if I can prove this right quick. I don't want this to go on too long, but the natural log of, or excuse me, I can do this. Is that what I want to do? The natural log of, no. Oh. Shoot, there's definitely some sort of, how about this? The log base A of B is equal to the log base A of E to the natural log of B. And that's the same thing. No, this is not what I want. Okay. I'm trying to prove this. How about this? The natural log of star is equal to the natural log of A to the power of log base A of star. Using log rules, that's log base A of star times the natural log of A. That's a logarithm rule. Okay, and then dividing both sides by the natural log of A. Okay, here we go. So that tells us log base A of star is equal to the natural log of star divided by the natural log of A, and that's what I wanted to show, and that's what I want to use here. So what I can do is rewrite this as the natural log of the cosecant of z divided by the natural log of 2. But the natural log of 2 is just a number. So all of a sudden, I think we actually can take the derivative here. This is the same thing as e to the square root of tangent of z times the natural log of 7. But that's also just a number. Minus 1 over the natural log of 2 times the natural log of the cosecant of z. And these are all things that we know how to take the derivative of. So I have the outermost function. That's e to the something. Taking its derivative, it's going to be e to that same thing. Times the derivative with respect to z of this thing on the inside. That's going to be, so this thing right here. I have to multiply by the derivative of this. But the natural log of 7 is just a number, so that's just going to drop, natural log of 7, times the derivative of 1 over, or excuse me, times the derivative of root tangent z. That's going to be 1 over 2 root tangent z times the derivative of the inside function, that's secant squared of z, minus 1 over the natural log of 2, the derivative of this inside function. Oh, look. I'm taking the derivative and I'm using bad notation. So this was me finally taking the derivative. So I almost said that the original function was equal to its derivative. That's false. So here we go. Now we're all on track. I'm amidst the process of taking the derivative. So that's going to be 1 over the cosecant of z times the derivative with respect to z of the cosecant of z. But that is the same. Okay, so cleaning up here. I don't know if we can clean up. So this object, like we have here, that's just 7 to the power of root tangent z. Root tangent z times the natural log of 7 times 1 over 2 root tangent of z times secant squared of z. And I can definitely make that look better, but I want it to focus here. This is minus 1 over the natural log of 2 times, another name for 1 over cosecant z is sine of z. And the derivative of the cosecant of z is the derivative of the reciprocal of sine. And you can do a little bit of work to show that that is going to be, oh my gosh, what is that? Cosecant minus cosecant of z times cotangent of z. Oh, these guys cancel. That's kind of nice. So, and also these guys become positive. The natural log of 2 times the cotangent of z. So to clean everything up, this is 7 to the power of the square root of tangent of z times the natural log of 7 times secant squared of z plus cotangent. Oh, and I'm missing a natural log of 2 over here. I'm trying to combine everything. So finding common denominators, I have to multiply this whole thing by the natural log of 2. Wait, no. I'm also just not, I can't do all of this, unfortunately. So we have the natural log of 7 times secant squared of z, all divided by 2 root tangent of z. Close parentheses, yeah, okay. Plus the cotangent of z divided by the natural log of 2. And I think I can call it good there. If you'd like, you can find common denominators and such. But I think this looks pretty good.